Now look at the characteristics of transition elements. Like I said earlier on, transition elements, they're actually metals, but they have unique properties that distinguish them from other metals. Some of the special properties are listed here. The first one there is metallic character. What did I say? Metallic character. That means its ability to have properties that other metals have. All transition elements are metals. They have very few valence electrons and therefore available valence empty orbitals. Hence, their valence electrons are mobile. What we mean by this is because the valence orbital is empty, there is space for the electrons to move from one position to the other. Because it can move from one position to the other, we say it is mobile. And those electrons that move from one position to the next are called mobile electrons. The metallic bonds between the atoms are very strong. Hence, they have high melting point. In other words, one of the characteristic properties of metal is that they have high melting point and also high boiling point. The second characteristics there is variable oxidation state. The transition elements exhibit variable oxidation states in their compounds because electrons in the outer s orbitals and the penultimate d orbitals are available for bond formation. In the first transition series, the 4s electron in the outermost shell are removed first before those in 3d. Example, consider the stepwise formation of ions by scandium below. Now you can see we have scandium here, and its configuration is argon in brackets 3d1 and 4s2. We have scandium plus. That means when scandium has lost one electron, it will have a positive charge. Remember that metals donate electron. Whenever an atom donates an electron, it will become charged. So the number of charges on that atom indicates the number of electrons it has lost. So if an atom lost one electron, it will have one positive charge, just as it is here. You can see that its atomic number has reduced by 1. And that's why we have, instead of 4s2 here, we have 4s1. As scandium, after losing 2 electrons, it will have 2 positive charges. That means it has lost 2 electrons, and that's why the configuration there is 3d only. There is no 4s electron there. Then, for scandium having 3+, it has lost all the valence electrons. The most stable oxidation state of scandium is scandium 3+. Like I said earlier on, all the valence electron has been lost for scandium having 3+ on top. It has lost 3 electrons, therefore it is stable at the electronic configuration of argon. Its configuration is that of the stable argon core. In zinc metals, the most stable oxidation state is Zn+. Zn+. What did I say? Zn+. Like I said earlier on, whenever an atom loses an electron, it will become positively charged. So zinc, being a metal, has lost 2 electrons, and that's why it has 2+ on top there. So the most stable oxidation state of zinc is that of Zn2+. It corresponds to the loss of the 2 electrons in the outer 4s orbitals. You can see the configuration here. You can see it here. 3d, 10, 4s, 2. Therefore, Zn2+, we have argon, 3d10, 4s0. There is 0 here, indicating that the 2 electrons here has been lost. So there is no 2 electrons attached to the 4s orbital. That's why we have 0 there. It has lost 2 electrons. The table on the board shows the oxidation states of the first series of the transition metals. You can see scandium, it has 21. The number at the subscript of each element shows the oxidation number. Scandium is 21, you can see it here. Titanium is 22, you can see it here. Vanadium is 23, you can see it here. Chrome is 24, you can see it here. Manganese is 25, you can see it here. Iron is 26, even though it's not written here. Cobalt 27, nickel 28, copper 29, and zinc 30. The third property or characteristics of transition metal is formation of colored compounds in the transition elements. There are empty or partially filled d orbitals. Hence, electrons can move into empty orbitals within the d subshell. Since the emitted radiations during such electronic transitions are in the visible region of the spectrum, their compounds appear colored. Example, copper 2 iron salts are blue, manganese salts are pink, iron 3 is brownish in color, and so many of them. Now, if you look at the transition, all these elements here are all transition metals and they have color. Like I told you earlier on, that transition metals have special properties that distinguishes them from other metals. And one of them is formation of colored compounds. You can recall in your qualitative analysis, when you add a reagent to a salt that contains any of these metals, these colors here will come out. For instance, copper, when you add a sodium hydroxide to a salt containing copper, a bluish color will appear. For manganese, pink, and for iron 3, brown. The reason for all these things is because the transition elements of all these transition metals have partially filled 3d orbitals. Because they are partially filled 3d orbitals, there is a transition of electron from one position to the next. Because of this transition of the electrons from one position to the next brings about these color changes, and they appear in the visible region. So whenever all these metals are subjected to irradiation, there is a transition of the electrons tend to transit, that is to move from one position to the other. Because of these transition metals have partially filled 3d orbital, they have color. But for some of them that have complete 3d orbital, there is no color change. For instance, zinc. Zinc has atomic number of 30, and it is colorless because it does not have any partially filled 3d orbital. The 3d orbital in zinc atom, they are all completely filled. So there is no transition, and therefore it is whitish in color, or you can say it is colorless. So it is pertinent to note that zinc 2 iron, copper, and scandium 3 are colorless because there are no empty orbitals of the 3d subshell. That is, their 3d orbitals are completely filled. Yes, when a transition metal has completely filled 3d orbital, there will be no color change. But if it has partially filled 3d orbital, there will be a color change. The fourth characteristic property is formation of complex ions. Transition metals form complex ions due to the presence of vacant or empty d orbitals in their ions. In this case, If a transition metal has a vacant d orbital, it tends to form a complex with another element. Their ions have high charges and small sizes, hence they form coordinate bonds with molecules or ions that are electron donors to produce complex ion. A complex ion has a central metal atom surrounded by neutral molecules or ions called ligands. Ligands are electron donors. Examples of ligand are water, ammonia, hydroxide ion, and cyanide. So what we are saying here is this, that transition metals have the ability to form complex ions, and these complex ions is made possible when there is a ligand surrounding that transition metal, because every complex must have a central metal atom at the center, and it is being surrounded by molecules or ions that can donate electron to the central metal atom to form a bond. Now those molecules that surround that central metal and that donate electron in order to form a bond is called ligands. So ligands simply means electron donors. So the complex relation cannot be complete without the ligands, because it is the ligands that supply electrons to the central metal atom to form bond. And the type of bond that is formed in a complex compound is called coordinate bond. It's called what? Coordinate bond. I hope you are following. Good. Let's move. Paramagnetism. The property of a substance whereby it is attracted into a magnetic field is called paramagnetism, while the substance is said to be paramagnetic. Paramagnetism is due to the presence of unpaired electrons in the d orbitals of an atom or ions. It is very common in atoms and ions of transition metals. Example is ion atom, ion 2 ion have 4 unpaired electrons. So now, this is also part of the characteristics of a transition metal, paramagnetism. When the valence electron, that is the electron in the outermost shell, take for instance for ion now, you can see that when we have ion atom, look at the electronic configuration. The 4s2 has paired electrons, the 3d has single 1, 2, 3, 4, 5, and then the 4s electron has only 2, and that 2 is paired. It is not paramagnetic at this stage, no. But when it is on ion 2, it has lost 2 electrons. You can now see that it has unpaired electron here. This, we have 1s2, we have 1, this is paired. The electrons in 4s2, you can see it here. Those of them in 3d, you can see here. Then the electron in 4s has disappeared, so it's not paired. So because of that, ion 2 ion is paramagnetic. So paramagnetism occurs when there is a presence of unpaired electron in the d orbital of that particular atom. Transition metal atoms or ions without unpaired electrons are repelled out of the magnetic field. They are said to be diamagnetic. So because they have paired electrons in the 4s electron, they are diamagnetic. So diamagnetism is opposite of paramagnetism. So when we have unpaired electron in the 4s electron, paramagnetism occurs. But if there is a paired electron, diamagnetism is said to occur. Catalytic ability. This is another property of transition metals. They are used as catalysts in most reactions. The catalytic ability of transition metals is due to the fact that they exist in several oxidation states. Hence, they are used as catalysts. For instance, a contact process that involves the production of sulfur 6 oxide, the process is called contact process, and a catalyst is used. The catalyst that is used in contact process is platinum, which symbol is Pt, or vanadium 5 oxide. Vanadium is a transition metal. So in this process, a catalyst is usually used, and the name of catalyst used, it must be a transition metal. So for contact process, platinum is used, or vanadium 5 oxide is used for the process. Another example is the Haber process. Haber what? Process. Haber process is a process that is used in the production of ammonia. We have two contact processes in chemistry. One is contact process. The second one is the Haber process. Haber process is a process that is used in the production of ammonia. And a catalyst is used. And that catalyst must be a transition metal. So for the Haber process, iron is used as catalyst. If you look at these elements that are used as catalysts in these two processes, platinum and iron, they fall in the transition series. They are all transition metals. So the reason why transition metals are used as catalysts is because they have variable oxidation states. They have what? Variable oxidation states. What I mean by that is this. For instance, iron. We have iron 2 iron. As mentioned earlier on, we have iron 3 iron. We have vanadium 5 oxide, and we have vanadium 3 oxide. So we can see that a transition metal can have 2 or more oxidation states. So because they have variable oxidation states, more than one oxidation states, that enables it to be used as catalyst. Nickel metal is used as a catalyst in the hardening of vegetable oils for the production of margarine. That's yes. In the production of vegetable oil, example of vegetable oil, you can see the production of margarine. Margarine is the butter you use in eating your bread. I hope you know what is margarine. Yes, margarine, the butter you use. Then, a catalyst is used in the production of that vegetable oil, which is used in the production of the butter you use at home or in your hostels. So the catalyst used there is nickel metal. And you know nickel is a transition metal. So you can see that in the catalytic property of transition metal cannot be overemphasized. They are used as catalysts in most reactions we use in the industries. Yes, because of that, they are used in such processes. And the reason for that is because they have variable oxidation states. Evaluation. Number 1, what are transition metals? 2, briefly describe the 5 characteristics of transition metals. 3, define I, paramagnetism. II, diamagnetism. 4, write the electronic configuration of the following atoms. Calcium, whose atomic number is 20. Zinc, whose atomic number is 30. Manganese, whose atomic number is 25. And iron, 26. Number 5. The electronic configuration of 5 elements represented by the letters P, Q, R, S, and T are indicated below. P, 1s2, 2s2, 2p2. R, 1s2, 2s2, 2p6. T, 1s2, 2s2, 2p6, 3s2, 3p5. Q, 1s2, 2s2, 2p4. And S, 1s2, 2s2, 2p6, 3s2. State which of them that I belongs to group 6 in the periodic table. I belongs to period 3 in the periodic table. I is strongly metallic in character. IV readily ionizes by gaining 1 electron. V contains 2 unpaired electrons in the ground state. Now let's solve it together. Number 1. What are transition metals? Transition metals are elements that fall in between group 2 and group 3 of the periodic table. Paramagnetism is the property of a substance whereby it is attracted into a magnetic field due to the presence of unpaired electrons. Diamagnetism is said to occur when the transition atoms or ions are without unpaired electrons and they are repelled out of magnetic field. When in a such situation, we say that diamagnetism has occurred. For number 4, we are going to write the electronic configuration of the atoms. The atoms are: calcium has atomic number of 20, and its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. If you calculate the total number of electrons, each orbital is calculated. You can see, let's check. 2, 4, 10, 12, 18, 20. You can see it corresponds to the atomic number. For zinc, that has atomic number of 30, we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. Let us check the total number of electrons. 2, 4, 10, 12, 18, 28, 30. It corresponds to 30. Manganese, that has atomic number of 25. We have 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s2. I hope you are following. Good. Let's check total number of electrons in the shell. We have 2, 4, 10, 8, 2, 4, 10, 12, 18, 20, and 25. Therefore, iron that has atomic number of 26, we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and 4s2. Now, if you look at the configuration, I want to point something out. You see that under normal circumstances, the 4s orbital is supposed to come before the 3d, but 3d came before the 4s. The reason is because once electron enters the 3d orbital, it pushes the 4s orbital up, so it will be higher than 8. So in that case, 3d comes before the 4s orbital. That is why you have 3d here and 4s2 here. We've come to the end of today's lesson. Thank you for listening. I hope you enjoyed the class. See you in the next class.